Hello, everybody. Welcome to your third Neuro Study Hall. I just want to mention a couple of things before I get started on today's learning technique and tutorial. At this point, ideally, you would have studied lectures, the first couple of lectures in your first week, at least twice by now. And it would be somewhat expected that week two material has been covered at least once, and maybe even a couple of week two's lectures have been covered twice. I'm not saying these things necessarily to pressure you, but just to give you an indication that if you're being consistent with your neuro studying, that's kind of where I would expect you to be at. So let's go ahead and dive into this week's study hall. First, we need to talk a little bit about last week, where we introduced drawing as a learning technique. And of course, drawing is one of my favorite learning techniques, especially when it comes to learning different scientific concepts like the ones you find in anatomy or neuroanatomy. Today we're going to kind of expand on drawing by introducing elaboration or elaborative interrogation. Now, just real quick, one of the great things about drawing as a learning technique is that it's really easy to incorporate other high utility or moderate utility learning strategies with it. You can think of drawing as kind of the base that we're going to build a foundation on top of. And some of the additional things that we're going to add onto drawing today is going to be elaboration. Now, many of you might use elaboration already and not know it, but I find that a lot of students don't elaborate enough when they're actually studying material. So first, let's just define what elaboration is, and it's maybe somewhat self-explanatory in the title itself. But elaboration is really asking yourself questions about the material you're looking at. Whether it's you're going through a PowerPoint or you're drawing, you're trying to see if you can come up with essentially the cause to the thing that you're looking at. An easy example would be that maybe you recognize tomatoes are a fruit and not a vegetable. Great, you know this fact. But how do you know this fact to be true? Maybe you say to me, well, tomatoes have seeds, and therefore that's why they're a fruit. And I think that's true. But with elaboration, you can still go deeper because in many ways, you're just kind of spitting off a fact. Tomatoes have seeds, that's why they're a fruit. Well, are there other ways to classify fruits? Is that the only way a fruit is because it has seeds? And so it's kind of like going down a rabbit hole of knowledge. How do you know this to be true? Well, then how do you know that to be true? This is an excellent way to monitor your knowledge, to see where you're at. And it also will allow you to gauge how easy it is for you to recall this information. And when you stump yourself, which in a lot of times with elaboration, you ultimately end up stumping yourself. You can't go any deeper. That's good. You take note of where you've got lost or where you lost confidence and couldn't answer something. And that's where you realize maybe a weakness or a gap in your knowledge. And then you go back and you try to fill that in. Now we're going to overlay elaboration onto drawing today. The drawing today is going to really highlight the power of elaboration, because another thing that elaboration allows us to do is really make strong connections between different ideas, especially because as we explain why things are connected, it allows us to understand their relationships better. We'll also take some time to see how elaboration can highlight differences between things. Not just how they relate, but also just how they are maybe not similar, which can also be an important thing in neuro or anatomy. Okay, so let's go ahead and dive into this now. This template was sent out to you, and so hopefully as you're going through this learning technique and tutorial, you have this in front of you. Today, I'm going to be posing a lot of questions to you. You can think of this tutorial as also kind of like a think aloud, where I'm going to be thinking out loud, and I might be posing questions that maybe I don't have the answer to them, or maybe I'm not giving an answer to them. And that's because these are kinds of questions I'm hoping you're posing to yourself. And if you become stumped, this is again where you should turn back to the PowerPoint, and to always turn back to your peers, your tutor, and your, of course, your faculty. So let's go ahead and get started. You should have this template before you where it's basically segmented into 3 sections, like a top blank section, a middle third that has 5 different panels, and then kind of a lower third portion where we're actually going to do some graphing here at the bottom. Each of these individual sections is going to allow us to see how what a neuron looks like, and to kind of have an idea of how an action potential occurs. A lot of students, when they look at an action potential or synaptic transmission, they tend to just look at that graph. I'm sure you probably know what graph I'm talking about. But let's look at the graph of an action potential, kind of in light of how basically ions move across a gradient. The first thing we're going to start with, though, is this very top panel here. And what I want to do first is I want to go ahead and let's just draw out a neuron together. All right. I should mention, if you don't already, I would suggest you have at least 3 or more colors with you as we draw this. So to get started, I'm going to choose the color orange, and I'm just going to draw a couple of rectangular boxes. Maybe I'll just do like 4. Maybe just like 4 rectangular boxes. Okay. These rectangular boxes are going to become our myelination. I draw them first because I feel like that helps me. Let's go ahead and draw our axon going kind of through these, right? So the axon in this section right here, we don't draw it, but it is technically being wrapped by myelination. So if you've ever done any kind of drafting, you might draw it like this with a dot to kind of indicate there's something underneath here or something wrapped here. Let's go ahead and draw our axon coming out this way, and we're going to draw our cell body. Now there's a number of different names for neuron's cell body, right? The soma, perikaryon, and again in neuro and in anatomy, if there's multiple names, you should probably try to know those. Now the way I draw these is pretty simple. I just make a couple of like loops, kind of looks like a star in the end. That's it. That's my cell body. This is not to scale, as you can imagine. So okay, let's maybe do like a little nucleus there. And for dendrites, let's just do some little like hair things kind of coming off of the cell body. So pretty simple. We're not quite done yet. Let's come back to the end here. So I'm going to draw something that kind of looks like a tree, I guess. And I'm going to draw these, I think, end feet or terminal boutons. Okay, so we have like our classic neuron here, right? This is what you would see in high school, what you would see in your undergraduate career probably. The question to you is, what are some other kinds of neurons? Do they all look like this? And this is where elaboration can come in, because we know not all neurons look like this. We know we have things like pseudo-unipolar neurons, multipolar neurons, unipolar neuron, which this would just be a classic unipolar neuron, bipolar neurons. And so again, we can already see that drawing is kind of our launching pad for the elaboration technique. What do I know about neurons? Asking myself, how many more are there? What are their differences in function? Okay, so those are questions for you to kind of address. But we need to label this a little bit, right? And so based on your ability, based on how comfortable you can label this, might tell you how much you know or don't know about a neuron. So again, we can call this the soma, right? But what are the other names for it? You should know some other names. We can call these little hair things dendrites. How about maybe we have, I'm going to highlight this little segment here in purple. How about this segment here? What is this segment right here? You could, I think maybe me using the word segment is making you think initial segment, which maybe we can call this the initial segment. But this here, I'm going to label AH for axon hillock. And again, it's kind of like in anatomy and neuroanatomy, they don't typically label or name something unless it has a function. That's for you to discover. You're labeling this axon hillock, you're labeling this initial segment. But what do these labels mean? So you have to dive deeper. Maybe you read that the axon hillock is where there's kind of like this summation of potentials that maybe allows for an action potential to occur. But even though you can spit that fact out, what does that actually mean? What is a summation of potentials? And that brings me to a couple other key topics that Dr. Skyba, Dr. CJ bring up in their lectures, right? Is that we have different kinds of potentials that can come up. Right, we can have temporal summation and spatial summation. And what exactly does that mean? And what did these look like? And can you incorporate these into this drawing itself? Okay, so I'm going to leave that for you to go back and look and kind of see how can I incorporate temporal and spatial summation into this. Now, one thing, we didn't really place this neuron anywhere in the body, and it does kind of matter whether you're saying, oh, this is a neuron in the central nervous system or peripheral nervous system. Specifically because we know that myelin is actually alive. It's a cell. So depending on where it's at in the body, we might call it a Schwann cell. Hopefully I'm going to spell this right. Could be Schwann. Or it could be oligodendrocyte. Question is, how do we know when we call it Schwann versus oligodendrocyte? You need to look into that. You also need to ask yourself, okay, well, if it's Schwann cell because it's in the peripheral or the central nervous system, why do we distinguish between the two? What are some differences between these things that allows us to say, okay, well, this is Schwann and that belongs in the central nervous system or that belongs in the peripheral nervous system? You need to go down that rabbit hole. This will allow you to prepare for those unknown questions. Well, number one, you don't know what questions are going to come up. And elaboration allows you to cover more ground while monitoring your knowledge. All right, so we know that this section here between myelination has a name. We call these nodes of Ranvier. Ranvier. I think it's a French scientist, and I'm probably butchering that name pretty good right now. And then we get to the end. Let's go to the end here, and we have a name for these. We have a name for these kind of buttons that I've drawn, and I think the French term that's used is terminal button, because it looks like a button. But you should go back and look to see, are there other names for these things here? And then what kind of connections do these make? You know, because over here you can imagine that there's probably maybe another another cell body it could be connecting with. It could be connecting with other dendrites. But could these terminal buttons be interacting with other parts of other neurons? Could these be interacting with axons? So this is where you need to find out, like, what are the kinds of relationships that terminal buttons can have? Is it just terminal buttons to other cell bodies, or are there other relationships? Okay, so I gave you lots of questions to think about with this kind of simple drawing. But what we need to do is, let's say that we actually had, I don't know, temporal summation occur, or spatial summation occur. Something occurred where we actually had enough conduction where we have an action potential now occurring along this neuron. Okay, and so for this action potential, it might look like this, where let's just say it starts here at the initial segment, and we know it's going to, quote unquote, bounce. It's going to bounce, right? It's going to look like this until it gets to this end here. And there's a name for this kind of conduction where it looks like it's skipping these myelinated segments, and that's, hopefully you remember this name, but that's saltatory conduction. But what I want to do now is, we need to kind of think about, well, what exactly is happening at each of these nodes as an action potential reaches it. What's happening just before, what's happening when the action potential reaches it, and what's happening after. And so we're going to use this image we just drew to kind of help explain an action potential. And we're gonna kind of draw out an action potential using these panels here. So the first thing I'm going to do is, let's pick one of these. I'm going to pick one of these segments to represent these panels. Okay, so what this means is that we are kind of taking this segment here and we're going to blow it up along these 5 panels. And we're going to do it temporally. We're going to do it over time, meaning that this panel is going to be representing this node just before an action potential hits, and just before it essentially depolarizes. And then this panel here is going to represent what happens essentially after we've already maybe depolarized, and what's happening after that. So again, we're kind of cutting in half a couple of these myelinating cells. So to kind of make this, what this would look like with this is going to look like this. We're going to have our, essentially what I call our myelinating bread, right? And then we're going to have the actual axon at the bottom there. And we're going to have a couple other things. So I'm going to choose the colors green and red to represent what I'm about to show next. Okay, so got my green and red. Now, we know that an action potential is it essentially comes about because of some movement of ions, right? And there's a number of different ions that can cause an action potential, but here we're going to stick with like the basics. We're going to stick with sodium, which I'm going to represent with green. Okay, that's not coming out. Try a different green. We're going to represent with sodium, and we're going to do it with potassium as well. Now, essentially, all along the node, we're going to have sodium and potassium ion channels, right? So if I were to draw, and so red for potassium, if I were to draw a closed potassium channel, I would do it like this, like two doors closed. And sodium, I would do the same thing. We have a closed sodium channel, and then these would be sitting in the membrane of the node. So hopefully you can see like this space here is representing this little space in here. Okay, so this panel here is supposed to represent this node at rest, meaning just, nothing's happening. There is no depolarization, no action potential has hit it. And so we could call this, let me do this in blue, we can call this resting potential. Great. Now, let's think about this in terms of our technique, elaboration. What do we know about resting potential? Well, we know that, maybe the name gives it away a little bit, that this cell is at rest. This particular segment, anyways, of the neuron is at rest. Do we know the voltage of the membrane at rest? And you could say, hopefully know that it's negative 70 millivolts. But here comes a big question. Why negative 70? And this is where you need to have an understanding of equilibrium potential. So why negative 70? How does that relate to equilibrium potential? Okay, and so the other thing is, so we drew out, something that represents a potassium channel and a sodium channel. But what do these ions actually look like when this part of a neuron is at rest? Well, we know that we're going to have a lot more potassium. So I'm going to do some red dots here on the inside of the cell versus outside. So outside the cell, we'd only have maybe a few. Right, so we have a disproportionate amount of potassium inside the cell versus outside. And then the opposite is true for sodium, where we actually have a lot of sodium. That's not popping up very good, is it? Let's see, this one works better. Where we have a lot of sodium outside the cell relative to inside the cell. You can ask yourself, well, how much? What is that discrepancy? And I think that typically it's something like there's like 40 times more potassium inside the cell than out at resting. And there's something like 12 times more sodium outside the cell than inside at rest. You don't have to know those numbers, but again, if you're going down that rabbit hole, it might be something you just quickly look into. Okay, but at rest, we know that there's more sodium outside the cell than inside. We know that there's more potassium inside than outside. And so you ask yourself, okay, why is this important? What does this even mean for me? What does this mean for something like an action potential, which I'm trying to understand? Well, it means that we've created something called a concentration gradient, something that I'm sure all of you have heard, and especially in your chemistry class. And that's something for you to look up. Well, what is a concentration gradient? And you can go further, but essentially it just means that we have more of one ion in something compared to another space, and that it's being blocked by some kind of barrier. And remember, you're right, in chemistry, we know that where there's less of something, right, where there's less salt in one space, more salt from another space is going to want to move into there. So we know, for example, that because there's more sodium outside the cell, it's going to want to try and move into the cell, but it can't at resting. And because there's more potassium inside the cell relative to outside the cell, we know potassium is going to want to try and move out, but it can't at resting because everything is closed off. We got a barrier. Okay, so let's go to our next panel here, right? So let's draw our myelin bread. Let's just draw a bottom part of the axon. So here, this panel is actually going to look very much like the first one. We're going to have our sodium closed, and we're going to have our potassium closed. And let's draw our axon membrane going through these channels. Okay, well, what's so special about this one? Well, this second panel, is going to represent what we call threshold potential. And at threshold potential, so keep in mind this first panel represented this node when nothing was happening to it. It was just at rest. But this panel is going to represent when an action potential has finally reached this node. So this action potential has jumped and is now hitting our node that we've been drawing. And so what's going to happen is first we need to see if this node can even carry on this action potential. And one way we know that it should be able to is if threshold is met. And so threshold potential means that the inside of this node, the membrane, at least is reaching negative 55 millivolts. So if we hit negative 55 millivolts, then we should have something happening. And we'll talk about that in a second. But again, we're comparing and contrasting these two panels using that technique of elaboration. But essentially, at threshold potential, the biggest change is that the cell membrane is now at negative 55 millivolts. But basically, potassium is still going to be largely inside the cell here, some outside, and sodium is going to be largely outside, right, the opposite of potassium, and some inside. Again, drawing it like this in a panel allows us to use elaboration to compare the ideas and concepts of resting potential directly with threshold potential. All right, let's go to the next panel. Again, let's draw our myelin bread. And again, I call it myelin bread because I think it reminds me of a sandwich. Let's draw like our quote-unquote bottom membrane there. Okay, so we hit threshold, which means that we hit or exceeded threshold potential. And so that means that we're going to have something else happen. And what's going to happen is that our sodium channel is actually going to open in this window, in this panel here. So I'm going to draw its space. There's a space now between it. However, our potassium is going to remain closed. And again, this only occurred because we hit threshold and we reached our threshold potential. I'm going to draw our axon like this, right? Where in the axon's membrane, potassium is closed. However, we have sodium open. Now remember from the first panel, we talked about how we created a concentration gradient in our drawing. And in the second panel, we still see that same concentration gradient. But we also created something else here too. We also created an electrical gradient, right? Because the inside of the cell in this panel here is more negative compared to a more positive outside. And we see that just because we have negative 70 millivolts here, right? The same can be said of this panel here and here, where again, even though we hit threshold, nothing is happening just yet. So the inside of the cell is still more negative relative to a more positive exterior. And I want you to think of this like magnets. That if we have positive ions on the outside of our cell, that positive ions are going to be drawn to a negative space. Just like a magnet, right? A positive pole will be drawn to a negative pole. And so not only will sodium be drawn to the inside of the cell because of its concentration gradient, right? We had more outside than inside. And where there's more of something, it wants to balance out, right? It wants that balance out. But sodium is also going to be drawn because it's being pulled by this electrical gradient, because sodium is a positive ion, so it's going to be drawn to this negative space. So we get this large and quick influx of sodium going into the cell. And we still, of course, have some outside. And it's this large influx of sodium going through its sodium ion channel into the interior of the cell that's going to cause what you probably know as depolarization. And a lot of times students, including myself, sometimes will just use the word depolarization and not think about that too much. But think of the word pole, like again in a magnet. In a magnet, there's two poles. There's a positive pole and a negative pole, like the North Pole and the South Pole, right? So we have depolarization occurring here. And the reason is we had this large influx of positive sodium ions. But what else is still in here? Well, we still actually have a lot of potassium ions. They haven't left. Their channel hasn't done anything just yet. It's still closed. So we still have a lot of potassium ions in here, more relative to the outside. And so when we say depolarization, right, you have to ask yourself, again, using that technique, what does this word mean? Is it just a fancy word? No, it's not. Remember our signs in our first two panels. We were positive and negative because everything was still in order. Positive, negative, because everything was still in order. We still had more sodium here than here, more potassium here than here. But here we get this influx of potassium, and at the end of this, it actually leaves us with a more positive inside than outside. The signs, they swapped, right? That's because they depolarized. The poles were flipped. And so because of that, we actually end up with something like a voltage of about positive 40 millivolts, a large spike there. And it's actually an ion going across a gradient. That's essentially, you can think of that as electricity. And so what happens is this node is now able to propagate that message through saltatory conduction. It depolarized, its interior rapidly increased in charge, and so it's able to continue the conduction to the next node. Okay, so now we're going to go to this fourth panel, and here we're going to basically show what is happening at this node after it's depolarized, after it's basically continued the message. So we're going to start with our myelin bread. So, okay, through elaboration, we're able to compare, and through this drawing, we're able to compare and contrast different stages of an overall action potential. Again, from resting, where nothing's happening, to when a node is actually has hit threshold and is about to depolarize and continue the message, to where it's actually depolarized and is continuing the message, continuing the action potential. And now it's sent its message along, it's already passed its message. But what happens now? Well, this panel here it's kind of going to look like the opposite. It's going to look like the opposite of this panel in a lot of ways, because our sodium channel has now closed, but our potassium channel is now open. And again, this was something I remember when I was first drawing this out. I was like, okay, why doesn't potassium open at the same time as sodium? Why is that important? And it's very important. And you know, what allows this to open quicker? Maybe that's not something you need to look into, but this is a fast acting channel, right? This opens up for like a millisecond. I think it's actually like a millisecond. Opens and closes pretty quickly. This is kind of slower acting. And so this takes about a millisecond to react. And so here we can see that this is closed because it opened and closed in a millisecond. This took about a millisecond to open, but now it's open. And so we get something really important happening. Again, remember that from this panel, we still had a ton of potassium inside the cell versus outside. And so now potassium wants to balance things out. So potassium is going to leave the cell now, right? It's going to efflux. It's going to leave the cell and flood this exterior space with potassium. So we're still going to have some potassium in here. But again, a lot is trying to leave. And of course, where is our sodium? Well, this sodium channel closed. And as a result, all the sodium that was captured here, it's actually still in here. There's still a ton of sodium in here. But here's the thing. And of course, we still have some sodium outside, always. But here's the thing. Even though this was slow to open, this stays open longer. This potassium channel stays open longer and allows more potassium to leave. It's not just open closed very quickly like sodium was. This opens after sodium, and it takes a little while to open. But once it's open longer. And as a result, we have this happen where our signs are going to actually flip back. And so we depolarized where the signs flipped, and now we're going to repolarize. So this is repolarization. Re meaning going back to, right? Returning to the original polar or original poles. So positive exterior, negative interior. But because it stays open and we lose so many positive ions, because we lose these positive ions, we're becoming increasingly negative. So basically the way I represent it here is that our charge is just going to be less than positive 40 millivolts. We're going down. There's no exact number that I have. We're just going down from positive 40 here. But again, you kind of think of the repolarization as the cell is trying to reset itself, right? Because again, you have to ask yourself lots of questions like, why repolarize? And it's because it's trying to reset itself. So then we get to our last panel here. And don't worry, I know it's taking a little while, but when you get to this third section, this third here, that goes pretty quick. So with this last panel, sorry, I'm running out of room here. With this last panel, we're still going to we're still going to show that our potassium is open, again, just to show that it's open longer. It's open longer than sodium was. We're still going to draw our sodium as closed. And so you can imagine that this last panel is actually going to look just like this one here. Again, where we still have potassium leaving the cell. There's some inside, and we still have a lot of sodium in here. Some outside. But at this point, because really in many ways, because potassium has been open for so long, we've lost so many positive ions, we've actually overshot where we want it to go, right? Because if you think about this as a story where, we started here, and we also want to end here. We want to get back to resting. But we kind of missed our mark. We were trying to get back to -70, but because the potassium was open for so long, we missed it, and we end up at about negative 90 millivolts. And so we missed it. We overshot it, and so we call this stage hyperpolarization, right? We went above, or in this case actually below, but we overshot it. So we still have, our signs still look the same as the previous panel, positive, negative, but we overshot it. And so my question to you is this: how do we go from hyperpolarization back to resting potential? How do we go from here to here? And a lot of students, and this was a question I had, like, how do we do that? And I used to say to myself, oh, it's the sodium potassium pump. Well, that helps to restore the concentration gradient, but does that really help us to go from negative 90 back to negative 70? And so this is where you would hopefully pick up your textbook or go to Dr. Skyba, Dr. CJ, and there's a key thing you should look into just a little bit, and it is mentioned, I think, in the slides, and those are leak channels. Leak like a hose has a leak or something. But how do we go from here to here? So through elaboration, you should be able to, from panel to panel, compare and contrast any one of these panels, their voltage, what led to their voltage, what is it called, what is sodium and potassium's relationship in any one of these stages. And hopefully these will make sense. Again, this is a kind of a timeline, really, right? From stage 1 to, we'll just say stage 5, all occurring at this node over different periods of time. But let's go down and let's kind of draw that classic, it's kind of a classic graph that I see a lot of students draw. We're going to draw that here. Let me raise this up a little bit. Okay. So I actually saw this was done in a book already, but I actually took this idea from my biomechanics past, doing position, velocity, acceleration graphs. Graphing, especially with something like this, can be extremely useful. So this graph is going to represent each of these panels over time. And it's going to, each of these individual boxes, you can see outlined here, is going to kind of tell us where the voltage is over time. All right. So to get started, let's just label a few things. So we're going to call this our 0 line. That's 0 millivolts right there. We're going to call this top red dashed line is going to represent positive 40 millivolts. Some might put down positive 35. And this one down here is going to represent negative 70 millivolts. So again, these are all millivolts on our y-axis. And then this here is going to be time. So you could put you could put time if you wanted to, but I'm not going to actually put any real units. Okay, so let's draw this out over time. So we know that at resting potential, we are simply at what? Negative 70 millivolts. So our line for our voltage would look like that. Just a constant negative 70. But we know that if an action potential or if something were to increase the charge of our particular node and increase it enough to where we hit threshold potential, we would go up like this. We would go up to hit this mark here, which we'll call this negative 55 millivolts. That's threshold potential, right? Negative 55, negative 55. Awesome. So we hit threshold potential, which means that our node can continue propagating this message, can continue this saltatory conduction, and will do so very quickly, right? Because once we hit negative 55, our sodium channels, they will act on that voltage. These are actually called voltage gated channels. So it will react and it will open, and open quickly. And it opens we get this flood of sodium entering the cell, lots of positive ions, and so we go up to this positive 40 millivolt line. But of course, we know we can't stay here because in our next stage, sodium closes, but potassium opens. And because potassium opens, we're essentially going to be losing potassium ions. So we're going to be going down from here. I'm just going to draw it down, right? And again, we're less than positive 40 millivolts, right? Less than positive 40 millivolts. And we're trying to repolarize, right? Get the signs back to the way they were at rest. We're trying to get back to our resting potential. But of course, because the potassium channels are open for a little while, longer than the sodium channels, we overshoot it. We lose too many positive potassium ions. But there's an issue, right? We're at this, we'll call this negative 90 millivolts. So the issue is, and for you to discover, how do we go from negative 90 back up to resting? How do we restore our concentration and electrical gradients? So I wrote that all down there. How do we restore our concentration and electrical gradients? How do we restore that? And the other thing I'll let you go look up on your own is what is our absolute refractory period, which I'll represent with this line here. And what is our relative? So relative refractory. And my handwriting's terrible, I know. And our absolute. Yeah, there you go. Refractory. What are those, and what do they have in relation to the panels above? So that's for you to discover. But again, with elaboration, you should be comparing and contrasting things. I would encourage you to utilize something like drawing as a technique to overlay elaboration onto. Again, you can create these things on your own. You can create and share with friends so that you're not maybe taking up too much time when it comes to drawing out. You can also find a lot of tutorials like this online. So utilize these, but then customize them to this specific neuroclass, to the content you find here. This is on one single piece of paper, covers a lot of material, and it can cover a lot more if you just layer onto it. But remember, elaboration allows you to compare and contrast concepts, allows you to ask lots of why questions. So don't just be satisfied with a certain answer. Keep asking why. Try and stump yourself. So that's all I have for this particular neuro study hall. If you have any questions about anything we did today, or about how to incorporate these techniques into other classes or other neuro content, please don't hesitate to reach out to me. And if I don't see you next week is Thanksgiving. Have a good Thanksgiving. Please don't hesitate to reach out if you have any questions also about tutoring. And go see Dr. Skyba, go see Dr. CJ, go to them with questions, go to them and ask if you can explain a process to them. Allow them to be another source of monitoring and keeping you accountable. Okay, thank you so much. Have a good day.